Yes, I'm very happy to be here, and I've enjoyed so much the presentations yesterday, and I hope today I don't ruin it. So I changed the title a little bit, but it's the same subject, how to improve forecast by identifying and deleting detrimental observations. And this is work that was mostly done by Dr. Tse-Chun Chen, who finished his PhD last fall, and myself. But I want to especially acknowledge the work of Daisuke Hotta, who did his thesis also on EFSO and PQC, but and Jim Young and Lien, who gave us the efficient GFS LITKF system with which we got our longest results. And especially Takemasa Miyoshi, who, when I developed the EFSO equations and I showed them to him, he encouraged me and us all to work together and develop the ideas like proactive quality control there. And Yoichiro Ota was a visitor at NCEP, and he implemented the EFSO and also implemented the first example of proactive quality control, which is the heart of what I'm going to show. And also Krishna Kumar, Jordan Alpert, and Cheng Da. So I would like to start with exceedingly simple ideas. This is a schematic of the classic data assimilation, and the purpose is to improve numerical weather prediction. And for that, we need to improve the observations with time and improve the analysis, the method of data assimilation with time, and the model with time, and they all have to be improved with the years and the decades, and that improves the forecast. And the analysis creates, combining observations and the forecast, the initial conditions for the model, and the model produces a 6-hour forecast, and this is the classic data assimilation cycle, analysis cycle, and then there are operational forecasts. So in this classic data assimilation, every 6 hours we make a new forecast. We get new observations that are at the same time as the 6-hour forecast, and combine them to get the new analysis, which gives the initial conditions for the forecast. So now let's consider new applications for modern data assimilation, and the impact of the data assimilation is in the quality of the analysis, which is much better than it used to be. So we can also use the data assimilation, and in particular the analysis, to improve the observations and also to improve the model. And now I'm going to talk just about the observations, but it's also important to how to improve the model. We will show how to identify and how to delete detrimental observations to improve the analysis and the forecast. And the idea is to use future observations to quality control the current observations. So in general, there are many observations that are beneficial, and and beneficial means that they change the analysis in such a way that the forecast gets better. So that's what beneficial is. So we will, yeah. But some observations are actually detrimental, and they may, instead of improving the analysis and improving the 6-hour forecast, they make it worse. So how to identify and delete detrimental observations? We use the observations in order to improve the current observations at 0 hours. We use the observations that are obtained after 6 hours. And so we combine the new observations at 6 hours with a 6-hour forecast, and that creates an analysis which is our best estimate of the truth. So in the rest of the experiments, we assume that the truth is given by the analysis that comes from the observations at 6 hours. So we don't do the full cycle, just create an analysis, which is all we need. Then after we do this, we go back to the t equal to 0 hours. So we check each observation now at 0 hours, and using ensemble forecast sensitivity to observation or the adjoint approach, FSO, we find whether it improved the forecast. So introducing the beneficial observation improves the analysis and the model, and this is proven by the fact that the 6-hour forecast is better, or it makes it worse. So it makes the forecast worse, and we then consider those detrimental observations, and we are not going to use them in general. So we delete all the detrimental observations and repeat the analysis at t equal to 0, assimilating only the beneficial observations. Yeah, and as a result, instead of having beneficials and detrimental observations, we only have beneficial, or most of the detrimentals are deleted. And as a result, both the analysis, which is the final analysis that we are going to use, and the model forecast improve substantially, as we will see in examples of 10-day forecast using the GFS LETKF system. So this is an example of the result of applying this EFSO estimation of beneficial and detrimental observations, and each observation is colored blue if it reduces the error, and it's colored red if it increases the error. So it's detrimental or beneficial, and the size is the impact of the reduction of the error, and I will discuss more later. So we can see that for example, at high latitudes over here, there is a bunch of many observations that are red. So they are detrimental. They happen to be detrimental modest wind observations, and this was when Yoichiro Hotta did this experiment for the first time. It was the first time that it was found that modest winds had detrimental episodes. So I'm going to show now the results obtained using the very efficient GFS LETKF system developed by Lien and Chen helped in 2018. And we did experiments for a month with 5 days for spin up, and it was in winter of 2008. And the model was relatively low resolution, but not too low, so that's no, not too low. But it's very, very efficient. So the data assimilation was the LETKF with 32 members, and the observations are the prep buffer data from NCEP, which means all observations except radiances. And the localization was 500 kilometers in the horizontal and vertical 0.4 scale height. And the inflation is the RTPP by Zhang et al. 2004, and adaptive inflation by Miyoshi 2011. And very importantly, we verified the truth using a completely independent reanalysis as truth, the CFSR, Climate Forecast System Reanalysis. So this is a system which uses real observations, not all of them, but real observations, and it's very efficient, and it allowed us to do the experiments that we did, which otherwise we were not able to do. So this is the difference between the analysis error using this proactive quality control that eliminates the 10% of most detrimental observations. And blue means that, and also this system is cycled, so one every 6 hours is followed by another 6 hours, so the improvements accumulate. So as a result, on the average, you can see that all the variables, U, temperature, moisture at low levels and middle levels are blue. So the analysis is improved globally for every variable, which is quite impressive, just the analysis. And now this is the most, the figure that makes me most happy, and made me most happy when we saw it for the first time. We separated the impact of deleting 10% of the most detrimental observations into 3 parts. First of all, this compares the difference between the RMS error, for example, for U at 500 millibars, the difference between the experiment and the control, which is the standard data assimilation. So 0 represents the control, the difference with respect to the control. And then we separate the total reduction, and this is 10-day forecast. So it's the average for 0 to 10-day forecast in the horizontal axis. And the blue is the total reduction of error, percentage error for the total correction. But the total correction is the sum of the corrections that accumulated from using it before, which is in green, and then the current or immediate correction. And you can see that this is the northern hemisphere, the tropics, and the southern hemisphere. And you can see that almost everywhere the most of the correction is not the current correction that corrects the current observations, but the accumulated corrections from past observations, and basically like 90% or benefit comes from the accumulated correction. So the accumulated cycle PQC can be done even without using the latest correction. So this indicates that we don't need to wait for the 6-hour new observations to come to apply it, because that will only add this top small correction. The majority is already accumulated in the past. So this can be done if it is cycled. It accumulates the benefits and it's completely feasible in operations. So we separated the total correction of cycling into immediate and accumulated correction, and most of the total correction is provided by the cycled or accumulated, the green line. And again, this indicates that proactive quality control is feasible for operations, even if we don't have time for an immediate correction of the future observations. So this was a very encouraging result. But then instead of rejecting 10% of the 10% most detrimental observations, Sechun also tried rejecting 30% and even 50% of the most detrimental or slightly positive observations. And this is the result. The blue represents what I showed before, which is rejecting 10% of the most detrimental observations. And then you can see green and red for the northern hemisphere are almost the same, but actually the 30% is better than the 50%. But in the southern hemisphere and in the tropics, 50%, for example, elimination of the most detrimental observations is the best, not in the northern hemisphere. So rejecting 50% of the detrimental observations improves the 10-day forecast. So the improvement basically lasts 8 or 10 days. And this is most true in the tropics, and which therefore it's the area which would receive most improvements from performing this. And in the northern hemisphere, 30% is best. And it's very surprising that 50% of taking away 50% of the least beneficial or most detrimental observation still gives good results. And why are there so few beneficial observations in FSO or EFSO? The results are very similar for both. So FSO studies found similar results and suggested different reasons that only like 55% of the observations were beneficial and not more than, much more than 50%. So, and some of the explanations were inaccurate verifying analysis or the statistical nature of data assimilation that would require this, and other inaccurate background error covariance and modes with different growth rates. We also, our results doing experiments suggest that the number of observations that are beneficial depends on the relative quality of the analysis and of the observations and the forecast. And if we, for example, if we here change the quality of the observations, which have an error of here it's 10 to the -5 standard deviation, and now they become worse until it reaches only 1. You can see that the worse the error, then the beneficial percentage goes from being well above 50% to basically 55%, which is typical of what we get. And similarly, if the observation, if the forecast, whose quality depends on how long the forecast is, the longer the forecast, the more beneficial the observations are. So we will have many beneficial observations if the quality of the forecast is poor, or if the observations are not accurate. So I'll quickly explain EFSO and show how, yeah. So the idea, which I'm sure you know better than I do, comes from a paper by Langland and Baker that says, suppose that you have observations at 0, and then you make a forecast, which in our case is 6-hour forecast, but it could be longer or shorter. And then we verify against something, so we have the error which is represented by this value if you don't use, if you use the observations, and if you start 6 hours earlier, you do not use the observations, and then presumably you get a total error which is larger. But for each what the genius of the original idea of Langland and Baker and my adaptation to ensemble Kalman filter is that we can estimate the difference using some units, so that which we use for total energy of the error. So this represents the total energy of the error, and you get this equation in which the matrices, as pointed out by Hotta et al., are already available from the ensemble, and this is a long vector of observational increments, so we can assign to each observational increment the corresponding reduction or increase of the error if we have a beneficial or detrimental observation. So it's very efficient because most of these matrices are already computed, and it gives you for each observation. So EFSO is a linear mapping from each observation to the 6-hour forecast, and negative means means that the observation reduced the forecast, so beneficial, and positive means that the observation increased the forecast error or detrimental, and it's efficient. The matrices above are already computed, and there is no need to, and this is the most amazing discovery that we made. There is no need to repeat the analysis without the detrimental observations. We simply apply the EFSO corrections from this equation, which is what Hotta et al. Did and